Give this one a shot. Tell your neighbor.
Because I feel like that's very important. But I don't think it is. I think it's like, no. I mean, in general, maybe. I don't think this. Does the fact that it has a core matter? So, like,
That have a cord.
Like if it's like cordless or not, does that matter?
Doesn't matter.
Yeah, I still know. It's for your safety.
Correct answer is B. Buster Brown. Okay. So here, this diaphragm is vibrating. So this coil of wire experiences a change in magnetic field, induces a current, an alternating current that's sent. So that's generating electricity, small amounts, which is sent to the amplifier, which is amplified and then sent to the speaker. So you have current going through this magnetic field, experiences a force, vibrates back and forth. That's how a motor works. Okay. All right. Number 11 on the worksheet, we did not really discuss in class. So I'm going to need a volunteer for this one. All right, come on, Bennett.
Wait, I have to crank this.
Yeah.
Oh.
There we go. Okay, come on over here. Okay. What Bennett's going to do is he's going to turn this at a steady rate. Okay. And what I'm going to do is I'm going to unscrew unscrew the light bulb and screw it back in. Unscrew the light bulb, screw it back in, and Bennett's going to tell us what he's experiencing as I'm doing that. So a steady rate, doesn't matter how fast.
That's easier. And that's harder.
Yep. Good. That's what I'm going for.
All right.
All right. So while the circuit is closed and the light bulb is on, it's harder to turn. Okay. The reason why is because now you have current flowing through wires, the wire loops, in a magnetic field. What happens when you have current flowing through a wire in a magnetic field? There is resistance, but that's not what I'm going for. That is true. Foundational fact number 2 says, Foundational fact number 2 says, if there's a If there is a current or charged particle moving through a magnetic field, then that will experience a force. Turns out that force will always be in the opposite direction of the way you're trying to move the wire. Okay? So it opposes, I consider this magnetic friction. Okay? So this is the energy that you have to put in to make electricity. Like you can't get something for nothing. Does that make sense? Like there will always be a force that opposes you from spinning those wire loops. Good with that? Okay. All right. Give that one a shot. Tell your neighbor. The correct answer is C. There are more loops of wire experiencing this change in magnetic field. Good with that? So, follow-up question. Talk to your neighbor. Correct answer is B. Okay. So some people think, dude, seriously, like all I need to do is just add more loops of wire and like I make more electricity. Like, yeah, but it comes with a cost. It's harder to push through. Like it takes more work. Okay. Conservation of energy, can't get something for nothing. Good with that? All right. Now,
Can you make parallel circuits with this, or only the other ones?
series. If you had
Like when it's spinning, can I put one loop here and one loop here, so it's parallel? That goes in circle.
like have two different loops spinning, sure.
Like I have a loop here and a loop here, and a magnet's like both.
Yeah, you could
So that would be a parallel circuit.
wire it like that. Usually they're going to wire it in series.
It's usually a series.
Usually, because it adds up the voltage. Like, you know, yeah, I mean, yeah, you could do either way depending on what you're trying to power. All right, so what I have here is an aluminum rod. Okay, got a little magic trick here for you. There you go, nothing down the rod. See that? Good. Okay. Now, what I have one thing that's magnetic, a magnet, and another thing that is not. Green's magnet, blue is not. Okay. So, magnet, not a magnet. Do magnets stick to aluminum? Magnets stick to aluminum? No. There's a green one not sticking. Okay. Now, I'm going to drop the non-magnet one down. Drops like a rock, which we would expect. Okay. I'm going to take the magnet that does not stick to aluminum, and I'm going to drop it down through here. Okay. Not magic, just physics. Okay. Here we go. Drop her like a rock. Oh. Okay. Some people are like, hey, why don't you do this? Okay. So there's both of them in there. I know. It's like, get away from me. All right. Now, what this is doing is, so this conductor is experiencing a changing magnetic field. There was no magnetic field. Then all of a sudden, it's like, whoa, magnetic field. And then as it leaves, like, whoa, where'd the magnetic field go? So it's always experiencing a changing magnetic field. This is a complete circuit. This is kind of a weird way to think of it, but currents are created going around the pipe like that. They're called eddy currents. I don't know if you've ever heard of an eddy current in a river. Technically, they're the parts of the river that, like along the bank, that kind of have like a scoop out of the bank, and like the current goes backwards, kind of spirals. Other places you could see it is like behind a rock in the middle of a stream or river, kind of like spirals behind it, kind of flows. If you ever like, I don't know, you know what I'm talking about, like, or like if you're canoeing, as you paddle it, you see the little vortices, little spirals. Those are little eddies. So,
What would happen if you flip the magnet over?
Great question. Let's try it. Here's one way going down. And then flipping it. Same thing. Because it's not really about which pole it is, it's the fact that it's changed, like this experience is a change in magnetic field. Okay, good with that? So these eddy currents are created, and because of that magnetic braking that we talked about, there's a force that's created that is in opposition to the way the magnet's moving. So that's what slows it down. Okay. You can experience this firsthand. So, got a copper pipe magnet. So when you do this, here's your number one rule. Don't drop the magnet. Okay? 2, before you get amazed and awed and wowed, put your hand underneath and then you can look down the pipe. Okay? Get to that. Put your hand and then go, wow. This goes first. Okay?
Oh no, I'm gonna drop it.
Don't drop it. Okay?
Oh wait, whoa.
It's super cool.
Like,
All right. As that's going around, I've got a couple other demonstrations that can be passed around. I've got some battery-less flashlights. Okay? This one, shake back and forth. Got a silver thing. There's a magnet. Then you got some threads. Sorry, you got some coil wire. Okay? So, figure out how that works. This one, as you squeeze it, the spinning thing's a magnet, and the sides have coils of wire. See if you can figure out how that's working. Okay? Okay, here's just a souped up version of what I'm showing you. I don't have that much copper. That's probably several $100s worth of copper right there. Yeah.
Wait, just get a bunch of pennies, melt them down.
Yeah. That's sort of illegal too.
No, it's not. It's for education.
That's illegal.
It's not illegal. It's just frowned upon. No.
Pretty sure it's illegal. It's just never enforced. Like the little stamp thing where you're like,
Like what? Like do they just sell it on Amazon? Big hyper teachers.
is it illegal to melt down pennies?
According to ECFR, any person who exports, melts, or treats 5-cent coins or 1-cent coins of the United States in violation of Section 82.1 shall be subject to the penalties specified in 31 U.S.C. 5111, including a fine of not more than $10,000 and or imprisonment of not more than 5 years.
Nope.
So it's just float?
No, because it has to be changing. It has to be moving.
Yeah, but like move it.
If you melt
Yeah.
one penny,
I mean, you can try it. Just don't drop the magnet. Like when it comes around here. What?
Actually, if I was for the last person, if I drop it, how would you feel?
Because you're not the last person. I've had this demo for years. I don't want it broken. Yep.
I was in the recorded classes. No,
Okay.
What are you doing? You didn't get it? No. Where did it go? Here. You didn't get it. Whatever. I don't know how it works.
All right. All right. Here we go. See, what did I do? Is there anything else I did? Oh, I remember that. All right.
Magnetic memory, or magnetic data
This is
storage,
a little
is a key
outdated.
component in computer operation. This depends on the ability of magnets to magnetize other materials, and the ability of those materials to
This is
retain
how-
the magnetization until forced.
This is how computers work. This is how hard drives, like a memory, works. This is worth knowing.
Change again by exposure to another magnetic field. Furthermore, an object can be magnetized at the north or south pole at either end. You may already know that data is stored in computers in a series of ones and zeros, a machine language more commonly known as binary code. But how can we represent a 1 and a 0 magnetically? Let's take a look.
Bit is the smallest unit of data storage. It can be visualized as a minuscule block that can be magnetized into a permanent magnet. Every red, blue, or gray block in this picture is a bit. The red blocks have north poles facing up, and the blue blocks have north poles facing down. These are what the computer recognizes as ones and zeros.
Okay, is everybody catching this? These are bits, computer bits, like bytes, like a bunch of bits make a byte. What? Yeah. Yep. Okay, so these, we can magnetize these. We can store data with this electromagnet, and that creates a really strong magnetic field here, and we can it magnetizes these blank ones. These are magnetizable, has some kind of iron, nickel, cobalt in them. This electromagnet, the current can be reversed, so it's going one way, creates a field going this way, and makes this way have a magnetic pole going one way, and then the current goes the other way. It can make the magnetic pole of this one go the other way. So one of these like represents a 0, the other one represents a 1. And so that's how you store data. How you read data is, as this passes by, this is the reader, and this just has a coil of wire in there, so it experiences a change in magnetic field depending on this, and induces a current. So it's kind of like a microphone and a speaker. You can record it with this. You can also read it from here. So this is also how credit cards work. The magnetic strip. After you swipe it, you have to go. If you go slow, it doesn't work. If you go fast, it works because this is experiencing a changing magnetic field when your card has a certain magnetic signature.
Can't you go too fast though?
You theoretically you couldn't go that fast. I mean, the credit card swiper might be broken, malfunction, but how fast you go through, there's no way you're going to be able to outdo that.
Is there a way you can go that fast? Robot?
Yeah, a robot, like
how fast? Like hypothetically, like give me a mile per hour at how fast that car. Or swipes per second.
I didn't edit it.
Swipes per second. This one swipe, just how fast? Yeah, miles per hour.
actually, I don't think you could. Like you would have to go like speed of light fast, which isn't.
You telling me if I harnessed this power and put it into this card and swiped it?
I think you'd run into other problems. Okay. So does this make sense how this is working? Sort of, kind of. Okay. So this happens at a hard drive.
A hard drive as a whole looks like this. Both the read head and write head are at the tip of the actuator arm. The motor of the disk and the motor of...
I got a better one. The hard drive is where all your memory is stored, all your data is stored on your computer.
So it's my brain. It's time guess. Why doesn't my head look like that?
Sign up for the Planet Fitness Black Card by March 15th. Get a free Amazon Halo View.
This is a real B&H customer story about Fred Smith here, turning lemons to lemonade. Fred, tell us.
An electric motor spins the hard drive's disk at exactly 7,200 revolutions per minute. The circuit board keeps the speed constant. And here's the crucial part: the actuator arms that hold the read-write heads. The ends of the arms are split, and right in the middle ride the disk platters. But the heads never actually touch the disks. The space between the head and the surface of the disk is 5,000 times thinner than a human hair. The heads float on a cushion of air created by the spinning disks. An absolutely essential cushion that prevents the head from crashing on the disk. And what a crash it would be. Talking about a crash is not only a metaphor. At these tiny scales, the weight of the heads really compares to the weight of a 747 airplane. A 747 airplane packed with 100,000 passengers, flying at 60 miles per hour, 1/100th of an inch from the ground. Ouch. There's no friction to slow things down, so the arms can move the heads to write or access data up to 60 times per second.
So JP, this is kind of how fast it's going.
Like, it's an electromagnetic system driven
No,
by two
this is how
forces of
fast they
nature,
go
electricity
all the time.
and magnetism, which makes the arms move back and forth across the disk at lightning speed. That's it for the components. Now here comes the data. The data is stored inside tiny concentric tracks on the
Here we
disk
go.
surface.
Here's the magnetism.
During manufacture, up to 200,000 of these tracks are created on the disk. Each track is divided into sectors. A map of the tracks and sectors in the printed circuit board tells the heads exactly where to read or write information. The surface of the disk is smooth and shiny, but look closer. It's way more complicated. A magnetic film on the surface memorizes all the information. The heads magnetize microscopic sections of the film and store the data in a sequence of ones or zeros.
Okay, this is the electromagnet. They're not shooting pulses of light.
The value of each bit is determined by the orientation of its magnetic field, plus or minus. And it doesn't take long for the bits to add up.
North, south
One
is what they meant.
high-quality photo can take up 29 million bits, spread across 12 different sectors of the disk. This sounds incredibly massive, but in reality, a stupefying quantity of bits can fit in an extremely small space. Each square centimeter of the disk's surface holds 31 billion bits. Now that's space saving.
This video was created 10 years ago, so it's like it's way more now.
Covers a phenomenal amount of information at speeds that defy.
Okay.
Is that how record players and CDs?
Yes. But did not magnetically, but yes. How do you what? It's crazy. They've been at it since 1957. So I know it's crazy. All right. So sad. All right. So one more demo, and then we'll have some fun. some more fun. All right.
Gotcha.
Got me. All right. This is used to be my magnetizer back in the day, upgraded since. But you have a single wire wrapped around two different coils. Creates when I turn it on, creates a magnetic field. Okay. Just take this iron bar rod, stick it in here. That strengthens and channels the magnetic field. You don't really see anything. But you take this aluminum cylinder, slide it down there.
Oh, that's fun.
Okay. So when you, oh, sorry, people on TV. There it goes. Yep, we got it now. All right. So when we do this, this creates a magnetic field. It's changing because all of a sudden there wasn't one, then all of a sudden, boom, magnetic field. And so this induces a current in here, creates its own magnetic field. It's in opposition to this. And that's what ejects it. So an application of this is if you've ever been to an amusement park that had like a magnetic starting roller coaster, not the ones that are like, but just like right at that, and like you're just flying. That's started by electromagnetic force, and then the braking system uses like this magnetic braking to slow it down at the end.
So
JP.
if there was a hole in that magnet and you had something made out of that coil that you could fit in there, would it still shoot out? So like if I drilled a hole through there.
Yeah, I follow what you're saying. Yes. There just need to be a whole circuit. So this one is a cylinder with a slice out of it. Okay. And we do that. So you got to get a complete circuit. So the orientation of that, you have to always have that. You couldn't be in like this. You have to be like that. Okay. Cool with that. All right. Now, what you're going to do is you're going to, round one, you're going to spin this yourself, but you're going to put your two fingers on either side of the light bulb and you're going to spin. That's round one. I would like everybody to try this. Experience alternating current firsthand. Okay? This doesn't hurt, it just feels weird. Okay? The faster you spin it, the more intense this is going to be. So if you're like, apprehensive, spin it slow at first. Okay? After that, everybody's gone through that, round two, we'll do it with the light bulb unscrewed. It is a substantial level increase. And then after everybody's done with level two that wants to do level two, we'll dip your fingers in water for level three. Okay? So, come on back.